The first crack appears at 3:47 a.m. local time. Nobody is awake to see it, but the instruments are. A network of seismometers placed by Apollo astronauts decades ago picks up something unprecedented, a deep, slow resonance moving through the lunar crust. Not an impact, not a moonquake. Something structural, something final. By morning, telescopes confirm what nobody wants to say out loud. The moon is fracturing, not chipping at the edge, not losing a small piece. The fracture runs across nearly 800 kilometers of ancient highland crust, and it is getting wider. Here is the first thing you need to understand. The moon is not glass. It is not a fragile, hollow shell waiting for the right tap. It is a world 3,474 kilometers across, with a mass of 7.34 times 10 to the 22nd kilograms. It survived 4 billion years of asteroid bombardment. It survived the formation of the solar system. It watched the dinosaurs die and said nothing. To break it, you need something extraordinary. So what are the realistic ways this happens? Option 1. A massive impact. The rock that killed the dinosaurs was roughly 10 kilometers wide. To crack the moon structurally, you need an impactor in the range of hundreds of kilometers. Objects that size exist in the solar system. They are rare. They are not impossible. Option 2. A gravitational encounter. A rogue planet passing through the inner solar system, something that happened repeatedly during the solar system's chaotic early history, could distort the moon's orbit and drag it inward toward a threshold called the Roche limit. The Roche limit is the most important number in this entire story. For the Earth-Moon system, the Roche limit sits at approximately 9,500 kilometers from Earth's center. Right now, the moon is 384,400 kilometers away, 40 times beyond the danger zone. But if something drove the moon inward toward that boundary, the mathematics of gravity would take over completely. Here is what happens at the Roche limit. The moon is not a single rigid point. It has a near side and a far side. When the moon gets close enough to Earth, the difference in gravitational pull between those two sides becomes greater than the moon's own internal gravity holding it together. Earth literally begins pulling the moon apart. The near side gets tugged harder than the far side. The moon stretches, it cracks, it fragments. This is not science fiction. This is how planetary rings form. Saturn's rings are almost certainly material from a moon or moons that crossed the Roche limit and were torn apart billions of years ago. Uranus and Neptune both have rings formed through the same process. Earth has never had rings in recorded human history, but it could. The physics is not special to Saturn. It is universal. Now here is where most people get the physics completely wrong. When the moon breaks apart, the pieces do not fall straight down like dropped plates. They were already traveling at the moon's orbital velocity, roughly 1 kilometer per second in sideways motion. That momentum does not vanish because the moon cracked. Every fragment inherits it. What you get is not a vertical rain of rocks. What you get is an orbital debris field. Thousands of pieces of former moon, each following its own slightly different path around Earth, each carrying mass, speed, and a trajectory. The small ones, gravel, dust, sand, hit the atmosphere and burn. The sky lights up from horizon to horizon, the most spectacular meteor shower in human history. Every night for weeks, continuous. House-sized and building-sized fragments survive the upper atmosphere and reach the surface. Each one hits with the energy of multiple nuclear weapons, concentrated into a single point of impact. And then there are the enormous ones, mountain-sized fragments. A piece 5 kilometers wide carries more kinetic energy than every nuclear weapon humanity has ever built, combined, several times over. These do not burn up. These arrive. But even the fragments that do not immediately fall are terrifying because of what they do to each other. They collide. Orbital mechanics guarantees it. Fragments in slightly different orbits, traveling at slightly different velocities, will intersect. Some collisions merge pieces into larger bodies. Some shatter them into smaller ones. Each new collision creates fresh debris. Each new piece of debris has its own orbit. The field becomes denser, more complex, more dangerous. This is a collisional cascade, a self-sustaining machine of destruction that runs on its own momentum. We already worry about a smaller version of this, Kessler Syndrome, the theoretical scenario where enough satellite debris in low Earth orbit triggers a chain reaction of collisions, filling key orbital zones with fragments that make further spaceflight nearly impossible. The Moon breaking apart would not be Kessler Syndrome. It would be Kessler Syndrome scaled by a factor that has no useful comparison. The sky above Earth would become a self-perpetuating system of destruction. No human decision required. And none of this has touched the ground yet. Before the first fragment falls, the oceans are already changing. The Moon drives roughly 70% of Earth's tidal energy. The Sun contributes the rest. Together they produce the familiar rise and fall of sea levels. And that rhythm is not a small thing. The difference between high and low tide at the Bay of Fundy in Canada reaches 16 meters. Global coastlines have been shaped by tidal action over hundreds of millions of years. Coral spawning cycles are synchronized to the lunar cycle, crab breeding patterns, migratory bird feeding schedules, human fishing calendars, and port operations. The tidal zone is not an edge effect. It is one of the most biologically active environments on Earth. If the Moon fractures and its mass spreads into different orbits, the unified gravitational pull that produced those tides disappears. You no longer have one large body pulling from a predictable location. You have dozens or hundreds of fragments, each pulling from a different position, each moving at a different speed, their gravitational contributions overlapping in patterns that shift continuously. Tides would not vanish. The mass is still there, but the rhythm shatters. Some coastlines might see weaker tides because the net pull is diffuse. Others could experience strange surges as a large fragment passes overhead in a new, unexpected orbit. Tidal timing would become impossible to predict without knowing the exact position of every fragment at every moment. The ocean would notice within hours. Within days, coastal flooding patterns would already be unlike anything in recorded human history. Within weeks, the planet's oceans would be operating under different rules. Not chaos. Physics still governs everything, but different rules. Rules that no living ecosystem evolved for. Now look up at that first night. The Moon is no longer a disk. It is an arc, a bright fracture across the sky, a dust trail catching sunlight at angles that produce colors no lunar light has ever made before. Several visible fragments, each casting its own faint shadow. The sky is crowded with things that were not there yesterday. It would be genuinely beautiful. That is uncomfortable to say, but it is true. The first night after the Moon breaks might be the most visually extraordinary thing any living human has ever seen. Glowing arcs, multiple overlapping shadows, constant meteor streaks illuminating different parts of the sky simultaneously. An artist could spend a lifetime painting just that first week. Beautiful, the way a fire is beautiful when it is consuming something irreplaceable. Because what is actually happening is that the machinery of Earth is coming apart. Not the rock, not the crust, the invisible machinery, the gravitational rhythms, the tidal clocks, the orbital stability that has been running quietly for 4.5 billion years. Earth has not yet felt most of it. That is the first layer. A familiar sky becoming something else, almost overnight. The oceans already answering. And above it all, millions of pieces of the Moon beginning the long, slow process of deciding where they are going to go. Here is the number that changes everything. 1%. The Moon's mass is approximately 1% of Earth's mass. 1% sounds manageable. Here is the reality. 1% of Earth's mass is 80 times the total water in every ocean on this planet. Every drop, every sea, every frozen pole. 80 times all of that. If even a fraction of that material entered Earth-crossing orbits over geological timescales, the consequences would not be measured in years. They would be measured in eons. But the first disaster is not what falls. The first disaster is what gets hit on the way down. Modern civilization does not run on oil or electricity alone. It runs on orbital infrastructure. More than 8,000 active satellites are above Earth right now. GPS navigation, weather forecasting, global communications, internet backbone, financial timing systems, military surveillance, disaster monitoring, aviation routing, search and rescue, not luxuries, operational necessities, systems that keep food distribution functional, power grids synchronized, hospitals and emergency services running at continental scale. Think about this for a moment. The device in your pocket knows where you are to within a few meters. That precision depends on timing signals from satellites synchronized to within nanoseconds, billionths of a second. Every rideshare pickup, every delivery route, every aircraft approach, every financial transaction that closes correctly. All of it running on a network of spacecraft moving silently overhead that most people will never once think about in their entire lives. Those spacecraft are now in the path of the Moon. At low Earth orbit, objects move at about 7.8 kilometers per second, 22 times the speed of sound. At that velocity, a paint chip carries the energy of a rifle bullet per gram of mass. A marble-sized piece of lunar debris punches through a satellite the way a bullet goes through paper. A fist-sized fragment ends a mission before anyone on the ground can react. Lunar debris would not politely avoid orbital infrastructure. Fragments spreading outward from a broken moon would threaten higher orbits first. Geostationary satellites, the ones handling the bulk of global communications, broadcasting, and weather monitoring, sit at roughly 36,000 kilometers above Earth. Some lunar debris could reach those altitudes quickly, depending on the geometry of the initial breakup. If a debris cloud swept through the geostationary belt, satellites worth trillions of dollars could be destroyed in a matter of hours. Then the cascade begins. Each satellite destroyed becomes its own debris field. That debris threatens neighboring satellites. Those collisions create more fragments. The chain reaction amplifies. This is Kessler Syndrome, the scenario Donald Kessler described in 1978, where enough orbital debris triggers a self-sustaining collision cascade that no one can stop from the ground. The Moon breaking apart would not be Kessler Syndrome. It would be Kessler Syndrome seated at a scale no model has ever seriously needed to simulate. The cascade does not take years to unfold. Some collision models suggest a significant debris event in a dense orbital zone could become self-sustaining within weeks. Not decades, weeks. Which means the first responders to a broken moon would not be planetary scientists on television. They would be satellite operators watching their assets fail in real time, one by one, each failure making the next more likely. Your GPS fails within hours of the first major satellite losses. Weather forecasting goes dark across entire continents. Airline routing loses precision. Financial markets lose the nanosecond-level timing signals that allow global transactions to settle. Most people do not know those timing signals exist. They will find out the moment they stop working. All of this before a single large fragment touches the ground. Now look at what happens as the debris field evolves over the following years. Fragments in orbit are not static. Gravity, atmospheric drag, solar radiation pressure, and gravitational interactions with other fragments continuously alter trajectories. Some pieces drift toward Earth. The rate depends on size, orbit shape, and breakup geometry. But it is never zero, and it does not stop after the first year. or the 10th. This is what separates the Moon scenario from a conventional asteroid impact. A single asteroid impact has a before and an after. It happens. It ends. Rebuilding begins. There is a direction forward, even if it is painful. A broken moon is not an event. It is a condition. The threat does not resolve after the first impact or the 100th. Fragments remain in orbit for years, centuries, potentially millennia, each one a future impact waiting for the right gravitational nudge. New collision risks emerge constantly as fragments interact with each other and with whatever remains of orbital infrastructure. Tracking networks would need to monitor thousands of objects simultaneously, running continuous risk assessments for every populated region on Earth. Evacuation planning would never fully conclude. Which coastline is at risk next month? Which ocean basin absorbs a major impact next year? No permanent answer ever comes. Here is what nobody in the disaster simulation accounts for. The broken moon does not distribute its catastrophe equally. A fragment on a collision course with Earth gives 2 to 5 years of warning if it is tracked early enough. If you have a telescope network, a space agency, and a functional rocket program, you attempt deflection. If you do not have those things, you watch the sky and calculate odds. The moon breaking apart does not level the playing field between wealthy and poor nations. It tilts it further in every direction simultaneously, and it does not apologize for it. Nations would fight over access to tracking data. Wealthy nations would attempt deflection. Poorer nations would have neither the data nor the means to protect themselves, and they would know it in real time. Now here's the piece that most coverage skips entirely. Mars. Mars has 2 moons, Phobos and Deimos, both tiny captured asteroids with nothing close to the mass needed to stabilize Mars's axial tilt. Mars pays for this in its geological record, every layer of it. Mars's tilt currently sits at about 25 degrees, close to Earth's 23.44 degrees. That similarity is temporary and deeply misleading. Mars's tilt swings between near zero and around 60 degrees over millions of years, driven by gravitational nudges from other planets with no large moon to resist them. When the tilt dropped near zero, the poles trapped carbon dioxide as ice and may have partially collapsed the atmosphere. When the tilt climbed, seasonal melting released enough gas to possibly support brief periods of liquid water at the surface. The Martian climate record is not a record of stability. It is a record of a planet cycling through entirely different versions of itself, unable to hold a fixed identity. Earth's tilt is constrained between 22.1 and 24.5 degrees over 41,000 year cycles. Remarkably narrow for a planet operating over billions of years. Without the moon, simulations by astronomer Jacques Lasker and his team, published in Nature, calculated that Earth's axial tilt could eventually wander to 85 degrees. Stand at the equator on a summer afternoon. The sun is high. Your shadow is short. Normal. Now tilt Earth to 85 degrees. The poles are pointing almost directly at the sun. The equatorial regions are tilting away. Your shadow stretches toward the horizon. The ice caps melt completely. The tropics freeze in winter. The growing regions that feed 8 billion people are no longer where they used to be. Everything that agriculture, infrastructure, and civilization were built on, the assumption of where the warm places and the cold places are, rearranges itself. This does not happen overnight. The timescale is tens of millions of years. But the process begins the moment the moon stops being a single stabilizing mass. Mars is not a theoretical warning. It is a planet we have landed on and read the geological record of. Ancient river systems, mid-latitude glaciers, layer upon layer of climate cycles written in dust and rock. Earth without a large moon trends in that direction, on its own schedule, following the same physics. Now look at the ring scenario, which is the outcome orbital mechanics simulations most commonly favor for certain breakup geometries. If enough lunar material spreads into a ring around Earth, the visual transformation would be unlike anything in human experience. A bright arc crossing the sky, present in daylight and luminous at night. At equatorial latitudes, nearly overhead. At mid-latitudes, crossing the sky at an angle. A pale scar that does not rise, does not set, is simply always there. Ring particles collide continuously. Each collision either merges particles into larger bodies or grinds them into finer dust. Finer dust scatters sunlight more efficiently, making the ring appear brighter, but also making those particles more susceptible to atmospheric drag. Dust settling from a lunar debris ring into Earth's upper atmosphere over decades could measurably reduce incoming solar radiation. Not catastrophically, but enough to shift agricultural baselines at a global scale. Particles knocked into unstable orbits by collisions would spiral inward and burn, not as an annual meteor shower, as a permanent, elevated background rate of meteors, every night, worldwide, with periodic larger events when bigger fragments re-enter. Every generation would grow up knowing the sky is active, that streaks are normal, that occasionally a tracked object requires a regional evacuation notice that goes out with the same mundane regularity as a weather warning. Imagine explaining this to a child born 15 years after the breakup. They point at the ring crossing the sky and ask what it is. You tell them it used to be the moon. They look at the arc with the same casual acceptance they would give to clouds. For them, this is simply sky. The old round moon, the one in every painting, every flag, every lullaby ever written, exists only in photographs. And photographs of a world that no longer exists feel less like history and more like myth. Saturn's rings are estimated to be somewhere between 10 and 400 million years old, geologically young, actively losing mass, and headed for disappearance within about 100 million years. Earth's hypothetical ring, built from denser, rockier lunar material rather than ice, would persist longer. Its particles would be more hazardous. Its evolution toward the surface would be gradual, sustained, and measured in timescales that encompass multiple rises and falls of human civilization. Living under that ring means every generation makes a quiet choice about whether to keep looking up. Not because the ring is invisible, because it is impossible to look at without knowing exactly what it is made of and what it is still capable of doing. That is the second layer. The moon does not simply fall. It becomes a debris field that becomes a ring, that becomes a permanent structure in the sky, one that rains itself down on everything below, slowly, generation after generation, until catastrophe becomes climate and wreckage becomes weather. Let's be completely honest about what this scenario requires. Something has to break the moon first, and in reality, nothing is about to. The moon is not secretly cracking. It is not drifting toward Earth. The opposite is true. The moon is currently moving away from Earth at 3.8 centimeters per year, away from the Roche limit, not toward it. In roughly 600 million years, the moon will be far enough from Earth that total solar eclipses, the perfect geometric coincidence of the moon's apparent size matching the sun's, will no longer be possible. The moon will look like a smaller disk in a bright ring, and the totality that ancient civilizations built mythology around will be gone. The moon is stable, reassuringly, stubbornly, historically stable. But that stability is precisely why the thought experiment is worth everything. The moon has been stable for 4.5 billion years, which means most people have never once been asked to think about what it actually does. It is background, decoration, something for poets, navigators, and romance novels. The thought experiment strips all of that away and forces a direct answer to a question almost nobody asks. What, specifically, does the moon do for this planet? The answer is more than most people expect, and understanding it changes how you see the sky. Start with the length of the day itself. The Moon formed approximately 4.5 billion years ago from a catastrophic collision between early Earth and a Mars-sized body called Theia. The impact was violent enough to vaporize both outer layers and throw an enormous amount of material into orbit. That material coalesced into the Moon. At the time of formation, Earth was spinning at roughly a 6-hour rotation. The planet was raw, mostly molten, and moving fast. The Moon was much closer then, perhaps as little as a few Earth radii away, and its gravitational interaction with Earth was dramatically stronger than it is today. Tidal friction between the two bodies has been transferring energy from Earth's rotation into the Moon's orbit ever since, pushing the Moon slightly further away with each year and lengthening Earth's day in the process. The current rate of day lengthening is approximately 1.4 milliseconds per century. That sounds meaninglessly small. Over 4.5 billion years, it adds up to 18 hours. The Moon has been Earth's brake. Without it, or with a Moon fragmented in a way that dramatically changed tidal coupling, the long-term slowing of Earth's rotation would follow a different path. The implications stretch into biology. Circadian rhythms, the internal clocks that govern sleep, hormones, metabolism, immune response, and cellular repair in virtually every living organism on Earth, are calibrated to the 24-hour day. Plant photosynthesis cycles, animal migration patterns, seasonal behavioral cues. The entire biological architecture of life on this planet was built around a day length that the Moon helped create. A different rotation history would have produced a different biology, possibly so different that recognizable life might not exist in any form familiar to us. Now put real numbers on the axial tilt. Earth's current tilt, 23.44 degrees. Variation with the Moon providing stabilization, between 22.1 and 24.5 degrees over 41,000 year cycles. Projected variation without a large Moon, potentially from near zero to 85 degrees over tens of millions of years, according to Laskar et al. Simulations published in the journal Nature. That is not a small difference. That is the difference between Earth as it is and something that barely resembles it. At 85 degrees of tilt, the geometry of the solar system rewrites every assumption about climate. The poles would receive more total annual solar energy than the equatorial regions. Ice caps would melt completely during summer. The equatorial zone would become a seasonal freezer. Atmospheric circulation, the system that distributes heat globally, drives weather, and maintains the temperature gradients that life depends on, would operate under completely different rules. The climate zones that exist today, the ones that define where crops grow, where deserts form, where forests develop, would migrate, merge, and in some cases disappear. The animals and plants alive today evolved for the narrow tilt range the Moon enforces. Remove that enforcement, and evolution faces a target that keeps moving. Mars, again, is the proof that this is not theoretical. The Martian geological record shows evidence of repeated extreme climate shifts, far beyond anything in Earth's history. Ancient river valleys formed during warmer periods. Glacial deposits at mid-latitudes formed during cooler ones. Ice-rich layers alternating with dust layers in the polar regions record dozens of climate cycles driven by tilt variations. The rock itself is a diary of a planet that cannot stabilize, because nothing is holding its axis. Earth's geological record is comparatively serene. Major climate shifts happen, but within limits. The Moon is a significant reason why those limits exist. Breaking the Moon does not immediately create a Martian Earth, but it removes the constraint that has kept Earth from becoming one. Now imagine Earth 2,000 years after the breakup. The immediate chaos has resolved into a new baseline. The largest early period fragments have already fallen or settled into long-term stable orbits. The civilization that survived the first few centuries has rebuilt differently. Satellite networks have been re-engineered to operate in debris-aware configurations, armored where possible, redundant by necessity, launched along carefully calculated trajectories that avoid the densest debris corridors. Launch costs are higher. Orbital missions take longer to plan. The night sky is permanently different. A ring crosses the sky at mid-latitudes. Not Saturn's ring, not clean, not flat, not made of ice. A rocky, irregular arc that catches sunlight unevenly, bright in some stretches and fragmented into dim, diffuse sections in others. Meteor activity runs consistently higher than any period in recorded history. Some nights, dozens of visible streaks per hour. On the rare nights when a tracked object enters the atmosphere at a shallow angle and burns across half the sky, people stop what they are doing and watch. The oceans have adapted to a new rhythm. The governing physics have not changed. Gravity is gravity. But the bodies doing the governing have. Tidal charts were rewritten over the first century after the breakup. Coastal infrastructure in some regions was abandoned. Some species that depended on precise tidal cycling went extinct in the first generations. Others adapted, because life adapts to the pressure it receives, rather than the pressure it expected. The word moon now means something different depending on who is using it and when they were born. Children ask, which one? The largest reassembled remnant? The ring as a whole? The three separate fragments that dominate the new sky at night? For them, the question is not rhetorical. They genuinely need clarification because their sky contains multiple answers. Language adapts to reality when reality changes permanently enough. Art adapts too. The ring becomes a subject. Religions that built cosmologies around a single round moon rebuild their symbology around the arc, the fragment, the scattered light. Some cultures frame the ring as wound, a permanent scar in the sky left by catastrophe. Others frame it as transformation, a reminder that the universe is not finished with its work. The same broken arc means something different depending on whether you carry the memory of the old moon or never knew it. That is where the most profound strangeness lives. The horror of a broken moon is not symmetrically distributed across time. For the generation that lived through the breakup, the experience would be traumatic beyond any previous frame of reference. The loss of the familiar sky, the terror of not knowing which fragment comes next, the collapse of infrastructure in days before a single large rock reached the ground, the realization, slowly and then all at once, that the thing you looked at your entire life without thinking was doing more work than you ever appreciated. For the 10th generation after, the ring is just there. The elevated meteor rate is weather. The shorter, irregular tidal rhythms are what tides are. They do not grieve the round moon. They never knew it. They have photographs and descriptions and the geological record, but it does not produce the same feeling that memory produces. It is history, not loss. This is what separates the moon scenario from almost any other catastrophic thought experiment. It is not just about destruction. It is about the disappearance of continuity. The ending of a relationship between a planet and its companion that had been running continuously for 4.5 billion years. Most people have never had to think about what the moon does, because the moon has always done it. Every human who has ever lived has woken up under the same tidal rhythms, the same axial stability, the same slowly lengthening day, the same reliable seasonal cycles. The moon's contribution has been invisible precisely because it has been continuous. It is the same principle that makes the structural supports in a building invisible until one of them fails. The moon is structural support. Breaking it reveals the architecture. And once you see the architecture clearly, the tides as ocean machinery, the axial stabilization as climate machinery, the tidal friction as rotational machinery, the moon stops being a decorative object hanging in the sky and becomes something else entirely. A counterweight, a governor, a machine that has been running silently above us for longer than complex life has existed anywhere on this planet. One final number worth sitting with. Some researchers argue that the tidal zones created by the moon's gravitational pull on early Earth were among the most important environments in the history of life. Tidal pools expose organisms to both marine and aerial conditions and cycles. They create selection pressure for organisms that can survive desiccation, temperature variation, and oxygen exposure. Fish ancestors adapted to tidal cycling may have developed the physiological preconditions for land-dwelling hundreds of millions of years before they actually came ashore. Remove the tides, and that selection pressure changes or disappears. The moon may not be incidentally connected to life on Earth. It may be part of the reason complex life on Earth exists at all. Breaking the moon does not destroy Earth. The planet is a rock orbiting a star, and it will continue to do that regardless of what happens to its companion. But the version of Earth that has existed for the past 4.5 billion years, the one with stable seasons, a slowing rotation, predictable tides, and a sky that has inspired and terrified and guided every human civilization that ever existed, that version is not recoverable. There is no rebuilding it. Once the moon breaks, the system that made Earth familiar does not restart. It transforms into something else, something that could still support life, something that could still support civilization, but not the same life, not the same civilization, not the same sky. The moon begins breaking at 3:47 a.m. By morning, the instruments have confirmed it. By that first evening, the sky has already changed. Every generation after that lives inside a countdown they cannot read. Not one countdown, thousands of them, distributed across every fragment still orbiting above. No alarm goes off when a new one starts drifting inward. You find out when someone runs the calculation, and then you wait to see if the calculation changes. It was borrowed. The moon was the collateral, and none of us thought to ask what happened if the loan came due.